Dear students, I'm your instructor Chem 524. I hope and pray that you and your family are well. In my last video lecture, I explained you crystal field theory. It's not any difficult theory. It is simply interaction of a metal ion with ligands. Please note that metal has electrons in it. Similarly, ligand has electrons in it. When ligands come close to metal, something should happen. What happens is the d orbitals of the metal which are degenerate, due to this interaction they split up. This splitting is different in different fields. For example, I'm taking on the very page 1 of my lecture 5 material manganese oxide crystal structure. If you will see in my notes, you will see that each manganese is associated with 6 oxygen atoms, and these 6 atoms are arranged in an octahedral way. This is what we mean that d orbitals are placed in octahedral field. This can be another field also. For example, the d orbitals can be placed in tetrahedral field. It can be placed in square planar field and all that kind of thing. So in each case, there will be a different pattern of splitting of energy. In case of an octahedral coordination compound, there are 6 ligands that surround the metal atom ions. In such cases, the ligand electrons repel electrons of the d orbital. This repulsion is more in case of dx square and dy square and dz square orbital. This is because they point directly towards the axis along the direction of the ligand. Now see, these are the d orbitals, and this is the ligand which is coming from top. Okay, so this is z-axis, this is x-axis, this is x-axis, y-axis. So the ligands are coming right on axis. So what should happen? These orbitals which are on axis, interaction of orbitals, they should become hot and they go up in energy. Please note, d orbitals, they have directional character. Okay, there are axial orbitals. For example, this one, dz square, dx square minus y square. These are 2 axial. And these, the other one, for example, dxy, this is non-axial. These are in between the axes. So naturally, when the ligand comes on this axis, this will go up. And if there is no ligand coming in this direction between x and y, then it will stay down energy. So therefore, I will take that we will get, as a result of this interaction of metal ions with ligand, and because of the directional character of the d orbitals. Okay, these d orbitals split up into two sets, T to G set and EG set. T to G set is dxy, dxz, and dyz. This remains lower in energy because no ligand is coming on these orbitals. No interaction is going on. The interaction is going on EG set of orbital, dx square and dz square. Dx square and minus y square and dz square with higher energy. Well, I want to say one thing here, that this T, which you will learn later on as well, this stands for 3, triple. So this is triply degenerate. These are three things, three orbitals which remain in same energy. E stands for 2, means doubly degenerate. That is, two orbitals or two states with same energy. Here in the diagram I have shown you. T to G orbital lower in energy, x square minus y square and dz square up in energy. Okay, now this is splitting energy. It's represented by delta octahedral. Okay, this is equal to, delta octahedral is equal to 10 dq. These are just units. Okay, if the value of dq is 100, then this splitting will be 100. Okay, reciprocal centimeter I, electron volt, or whatever is the unit of energy. Let me go next, and that is again the same thing in this on this page. I'm showing these the degenerate d orbitals after interaction with the ligand metal, T to G orbitals here. This is the splitting energy, and the division is, okay, this is stabilized T to G, goes down in energy. How much? Out of 5 parts, 2 parts it goes down, and this is 3 parts out of 5. That means 4 parts, okay, and this is 6 parts up there. So EG is higher energy set of the orbital and T to G is lower energy. At delta octahedral or 10 dq is the energy separation between the two. This is also represented by 0.4 delta octahedral T to G and 0.6. Okay. Well, I must say the process of splitting of the degenerate orbital, okay, due to presence of ligand, there is a difference in energy of T to G and EG level, and that is, as I said before, denoted by delta, splitting energy. Well, there are some ligands which produce strong field. It means they produce higher splitting and they cause large crystal field splitting. On the other hand, there are other which produce weak fields. Thus, the crystal field splitting depends upon field produced by the ligand and the charge on the metal ion. We can arrange the ligands in order of their field strength, and here I have shown you iodide is least, it doesn't create much splitting energy than bromide. Okay, iodide is less than bromide, chloride, cyanide. Now these are very strong ligand, EDTA. ammonia, ethylene, diamine, and cyanide, you know very well, is a very powerful. And people say that if you take just a bit of potassium cyanide, one is killed, finished. And this is because of the very strong. And similarly, about carbon monoxide is also famous. That when the people leave their homes or burning coal at night, and carbon monoxide keeps coming, and they do not know, and the whole family is expired because of this very poisonous. Because it is very strong. When it goes, it is inhaled. It it starts reacting with the iron. Now, D1 in octahedral crystal field. Okay, I think I have already explained you much. Here I'm just showing the ground state of that. Okay, in ground state, we'll put that one electron, D1 electron here, not here. So this is called ground state. And this is higher energy state. Okay, when this electron is here, it's this excited state. So there were two states. One is the ground state configuration of D1. I will represent it with T2G1. T2G1. Okay, T2G1 in group theoretical notations. Please, I haven't given you any lecture on group theory, but take it for granted that this is how we represent it. In group theoretical language or notation, it is represented by capital T and 2. Same thing. And here instead of writing 1, we write 2. Remember, this is spin degeneracy. 2 is spin. If there is one electron, unpaired electron, so spin degeneracy becomes 2. 2s plus 1, okay, become equal to 2. Okay. D1 free ion ground state term you already know very well. You can easily find it out. Okay, this is the, okay, doublet D. This is the ground state term symbol. Later on, right now we are putting D1 into the crystal field. Then I will be putting this later on in my next lecture, D2 in the crystal field, and see what happens to this energy state. Excited state is this, which is EG1. So I have written here, excited state configuration of D1 is EG1. In group theoretical notation, it is represented EG. And there, of course, we will put the spin degeneracy. There is one electron, so spin degeneracy is equal to 2. Here I have explained you where from this 2 spin degeneracy is coming. Remember, you know about this formula. Spin degeneracy is 2s plus 1. So 2 plus 1, okay, 2s plus 1 equal to 2, and then S capital S will be equal to, it will become equal to 1. So remember, spin degeneracy is also number. This is very easy, straight away very easy to find out spin degeneracy. Just find out how many unpaired electrons, add 1, and that will give you. In this system, there is one unpaired electron. So what is the spin? 1 plus 1 will become spin degeneracy. So this is what we have, the 2, 2, 2. Yes, spin degeneracy equal to expected number of spectral bands. Very easy. This is what we are learning in this 524 course, Spectral, how spectra is produced. Now you can see Okay. This is T2G state. And from here, if the electron goes up, then I will represent it like this. T2G, from this configuration, it goes to this. So this transition, it will require some energy. How much energy? Okay, that is reflected in the spectra when we take it. And see this one. This is the spectra of D1 system, and here is the energy. Okay, it is at 500 nanometer. Okay, and this is the visible region. You can see. Okay, this is I think blue light wavelength. So this is how this. So in this system, we predict there can be only one band, and you can see your books. It gives only one band. So, my dear students, you should know what I'm teaching you: inorganic electronic spectroscopy. Spectroscopy. Here is the spectra which has come, and we are able to explain it. Hopefully, in my next lectures, you will understand things more. Thank you.